So, hello. So I'm skipping because of the time my introduction. I'm Director of Research and Development for a German company called Novatec Consulting near Stuttgart. And we heard today quite a few aspects about what I want to talk about today as a practical talk about a real project I've been doing in the last years, which had the task to move an existing Java Enterprise transactional application onto a big data architecture in the cloud, simply because otherwise the company would stop being in business. So we're talking about going from a rather traditional monolithic application typically developed in, say, Java Enterprise with a layered architecture with its own database, onto something that could be described cloud ready. It's not a cloud architecture in the way that is described by Professor Lyman, for instance. It's simply cloud ready in the way it runs there. So as I said, it's a practical experience. We worked on it since December 2013. We started to develop the actual new architecture in March and ended in September, exactly as we planned. It was 11 years effort. So this talk is not only about doing this transformation, but it's also about the rather interesting consequences for the business about their requirements. So why bother at all? I mean, I've heard it many times. People say, you shouldn't do anything with transactional software with big data. This is a completely different kind of software. Well, technically, yes, big data developed out of completely different requirements, but actually, I'm saying big data is not a pile of technology. Big data is a diagnosis. It's a diagnosis of problems that an application faces that it cannot be handled with traditional architecture and technology. And this is very high volume, very large variety of data formats, and a high velocity of data intake and of analysis requirements of this data or usage requirements. So, on one hand, your application that's running in a bank, in an insurance company, or in an automotive industry might have a growing scope of new partners, new customers, larger markets, and suddenly the application stops working simply because there is too much data for the old architecture. Or you have a stiff competition. I hear this all the time, that somebody says, why do you take a week for your data warehouse ELT process and analysis? This company does it in 5 minutes or in an hour. So, big data architecture technology seems to be promised to lift an existing application to the big data world, but there's a high price. And I want to tell about this price today. I hope I come to that point. But the interesting bit here is the business people think they have learned it in transactional properties with ACID properties. So they hide all the difficulty of distributed computing, of specifying requirements in a distributed world, by simply saying all has to be atomic. And they spread logs and other things, business logs, technical logs, all over the application just to be sure not to think about this. But if you're going to a distributed cloud-native architecture, then the emphasis comes on concurrent execution. So let me talk about the product that we transformed. Well, it's a semantic middleware to provide information logistics. Now, anybody has an idea what it does? That's fine. Let's show what it does in steps. The first thing it does, it has agents collecting business information, say, of Daimler, the whole shared drive of all the documents they ever collected, or all their databases, or all their internal wikis and intranet. It takes all this information and imports them in one uniform data model in one master data store. That's the first step. That's a big task by itself. Then the next thing is this data is unconnected. In a relational database we do have foreign keys, they have technical relations. Well, we're interested here because it's semantic software in the content relation. So a lot of applications, analysis applications, run over this and connect all this data by contents. The easiest example is if you have, for instance, a PDF file with a meta attribute, author, which has my name, and there is maybe a construction document in a relational database that has a name that is also my name. This software would simply say these two documents belong to each other. They have a certain relationship that has a value to know. And the next thing is, once you have this, you get this picture. You have different data stores, and you get a mashup of information. And this information is connected by reasons why this information has a certain relationship, a value to know that this one and this one have something in common. And then you can query about this. You can go into this graph and say, or is it the independent graph? Okay. Maybe the battery lasts a few minutes longer. It simply stopped, I switched off now. Alright, so to come to the point, what you do is you query this graph, you work through this graph, and for instance, what you can do is a search steroids. You can say, oh, if I have this construction document, what other documents I don't know about, I don't know how to query them, do have a relation. And here's a practical example that really saves money. You get all these different car constructions with their parts lists, and there are associations to certain normative documents about, say, a screw. And because they are now linked, nobody knew about this connection, they realized that different platforms of car use the same screws. They have different part numbers, but they have the same kind of screw in there, so suddenly they realize the same supplier supplies small parts of this screw for 4 cars, for 4 platforms of cars, and say, could turn this in a big order and save money on it. Alright, what's the problem? Why should we concern about transforming it? The problem was, the previous implementation was Java Enterprise, best practice. It was layered architecture, very fine, it took me a day to understand the whole software. The algorithms were huge, big pieces of software, and there was a clustered Java Enterprise, it was JBoss, it was a clustered MySQL or similar relational database. It has Lucene, so it was all good quality. The only problem was, it did not scale. So this software, because of the complexity of the analysis of the graph, stops at about 2 billion relations. Now, the customer got customers' clients on this side who wanted to store petabytes of data in the system, because then they got the business value out of it, because nobody knew about all this data, but this software could discover it. The problem was, we had to scale up a factor of 1,000 in size and keep at the same speed. So, we measured, for instance, to show the scalability issue, that in a moderate data size, this was 900 million records, which is not really large. 95% of the whole import time, and this is my concern today, not queries but import time, was spent in comments. The system was 95% of its time completely idle. All the different threads, all the different cluster nodes were simply pulling a number and waiting to be served at the database. And so the system simply stopped for all practical purposes. So we are facing 2 killer problems here. The storage architecture did not scale at all, and the application design also did not scale. So to do such a transformation, the last thing you want to do is to jump into action. So the customers, developers simply say, okay, we have to change JBoss to Spring, and we have to use Elasticsearch instead of Lucene, and we're using a graph database. We have a layered architecture. We simply replace the persistence layer by a persistence layer for graph databases. Everything is good, right? What happens is you do change your architecture without knowing why you change it. So the first thing that we did was a workshop to understand the ideas, the reasons, the architectural decisions behind the current architecture. We did runtime analysis to understand why is the system so slow. We did code reviews to confirm why it is really so bloody slow. Then, very important, we locked the original developers in a cupboard. We showed them out of the room. We tell them, you come back when we are finished with our pilot. Imagine you have developed the old software and somebody like me comes in and says everything is wrong, everything is bad. This is not a good working environment. So please continue with your maintenance of the old version. We show you the new results and then you can continue on that basis. We did a plan, we did a pilot implementation, took us 4 weeks, and then everybody was shown into the room again. The new strategy was scalability, 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 and then quality of the analysis. It's very simple. If the analysis gives worse results, if the graph is not as nice, as useful as it could be, but the software does not run at all, it doesn't sell you a single copy. Strategy was first, decomposition of services. I mean, this is standard. Then we took this import service, which was a huge algorithm normally. It says, collect statistic information about all the documents in the database. All the documents in the database, horrible. Then select candidates for relations, also horrible. Then compare with the actual relations and then filter these relations. All right, next slide. 5 minutes. Okay, all these algorithms were simply very complicated, so we say these doesn't scale. So we split up the algorithm in steps, in computing steps. Each of these steps was meant to be one service that we chain. Then we wanted to allow analysis plugins, so it was easy to come and go with different services for analysis to like experiments. Then we used the SEDA model to compose everything in a topology of microservices. I'm coming to that in a minute. And in the end, we want to put everything in the cloud. So our development team...
You will get new values.
Okay, I can speak. I can speak very loudly. So everybody hears me?
No.
All right. I want to put
the phone. You can use the mic.
Alright, so good. So in the end we want to put everything in the cloud because we at Toenne as a development team used 50 servers in the cloud for load testing, for everything. So the SEDA model, everybody familiar with the SEDA model? Probably not. So if you're looking into enterprise patterns, this is the pipes and filter pattern. The main idea is you have microservices that are connected by pipes, by queues, and that are very selective if they take a message out of a queue or if some other stage should use this. And we use this to build computing steps. Each of them had transactional borders over all the plugins put into this one step, and it had an automated persistence. So the plugin developer for analysis like matching keywords, which is trivial, or analysis like natural language processing that understands the structure of sentences, which is really complicated, all of these were implemented functionally. They only produce deltas of the graph as an output, and automated persistent puts them in the graph database in the end. And we as a database use Titan. This was today not mentioned, but we use the database Titan to very good results. The only problem is that Titan, the developers were bought by DataStax, and this product is there for all practical means. Then we use the Cassandra as a data storage behind it, and Elasticsearch as a cluster. And everything was done in Spring, so absolutely no framework whatsoever, just Spring and directly our application. So, what is the benefit of such a structure? I can show you a simple picture. Let me go ahead into my backup material. So, a topology that we create with this SEDA model could be that we have an import API, then we have different stages that are put on different computing nodes, and everything was done as needed for higher scalability. So we created very large topologies that could have a chain of 5 to 7 steps, microservices, and 50 of them in parallel if needed. Okay. Okay, what was the benefit? First of all, we could group all these algorithm steps as the resources needed. Natural language processing needs a lot of memory, but we wouldn't want all the others run on a machine with a high amount of memory because it's much more expensive. We could adapt the number of instances of this chain of services as we need so that we get a very good throughput and a very good answer time. We could achieve the best possible data locality as graph database caches. And what's important, we are not bound to one technology. If we would do this in a container technology, we were bound, say, to Java. But the natural language processing tools were written in C++ or I don't know what. It's a completely different programming language. And so the stages do have contracts on their pipe stands, and if a stage is written in a different language, nobody cares. And we have a single source of truth for the optimization of the database. For the project benefits, I think I skipped this because of time. So we have, all this was very nice. We were, within 6 weeks, we were up and running, could do load tests, show that the overhead of the whole architecture is below 1%. The stability was excellent. We had full availability of the system. We were pretty happy. The only problem was the system was as slow as the old one. Why? The problem is that the business defined their algorithms, always ACID ideas, with transactional thinking, with maximum security. Don't ask me these questions, the type of requirements in mind. And here are 2 examples why this is killing a distributed computing system. One is uniqueness of relation. Imagine the example I gave. Andreas Toenne is the author of a document and also is mentioned in another relational record. So, if this record and this document come in parallel in the system, they are, of course, imported on different nodes. And if these nodes don't know about each other and just work in parallel without any synchronization, what happens is we get 2 relations of this kind. Because both relations are bidirectional, and we have 2 relations about the same statement. About the statement, there's the same author in 2 documents. And this would, by semantics of this graph, overemphasize this relationship. So this is, as a quality, is a quality different. So, the author of this requirement, very intelligent man, very smart, but he simply said, okay, there must be a new uniqueness constraint on this relationship. So in the database, they had actually a uniqueness constraint on the database, on this type of table, and they did very short transactions. They started a transaction, write the relationship to the database, commit, and if there's no exception on this uniqueness constraint, this relation stands, otherwise they don't write it. Now can you imagine if we import, say, 100,000 documents, each creates about 1,000 connections, this is a statistical normal number, and you have for each of them 1 commit. The system is doing 99% of its time commits, it's not working anymore. The other one was also interesting. All the semantic algorithms need statistical information. But how do you compute the number of distinct words, or the count of each distinct word, in a distributed database, effectively? You have to use simplest counters, which is a bottleneck again. So this did not work out. So what it said is, okay, if scalability is the only reason this company stays in business, we have to drop asset. We have to go for something like eventual consistency, allow errors, allow quality defects to a certain amount, so that the software is fast enough and good enough still. So it's a balance. This gives us about 6 months of retreat fights of the business, of course, because they say, if I don't get that, I at least want to have that. If I don't get that, I at least want to have that. So we were fighting 6 months with them to go down with their synchronization and consistency issues. Now, how do you get away? How much time do you have?
-1.
I started very late. All right.
Okay, 10 minutes with questions, okay?
Good. So, the key point is, how do I get away with eventual consistency at all? We've heard today the CAP theorem. My statement is the CAP theorem is just a re-excuse. Because if I go for enterprise enterprise systems, not for distributed systems like Google. If I have a rack with all my servers in here, partitioning is a very rare occasion, and it's a defect anyway, it has to be repaired. So consistency and availability of the CAP theory in such a scenario is not the real problem. What's the real problem is that as soon as I start to want to have higher levels of consistency, I need kind of agreement between all the nodes in my database. So we heard about the quorum consistency level during the morning. Quorum means the majority of the database servers of the Cassandra nodes need to agree on the write or on the read that they have the same data. This is consistency at this level. So that means we have to talk with the database nodes all the time. And this slows down scalability so badly, we tried it. It slows it down so badly that we said, we cannot use the system, we cannot sell it to customers, so let's drop the consistency for a certain time and go for speed. And here's a number to show how bad this can be. We measured this in a cluster of 15 servers. We have the need to have unique special words, concepts, important words in our graph. And to make them unique, we need to have a unique record for that. So we need to acquire a lock in the Cassandra database to write this one record and get an ID for it. It takes about 40 milliseconds in Cassandra to do this. So whatever you're doing, you can create at most 25 unique words of this kind in the Cassandra database. You cannot be faster. If you have more servers, you're slower. So we said, doesn't work. Since I don't have much time, I will go over briefly over it. This shows the whole picture of the consequence of eventual consistency. Imagine you have two data records coming in on different servers. Each of these import servers does a persistence of the record, an indexing and elastic search, and then computes for 10 or 15 seconds the relations. All this is done in full parallel, and they're writing the information in Cassandra Elasticsearch. And this one is not seeing the other results until the eventual consistency has been healed. And practically this means 40 to 100 milliseconds if everything is in the same way. But this is only part of it. This is Cassandra. Elasticsearch has a bulk refresh, replication mechanism. There's a refresh time, and this is normally 16 seconds. And we put it down to 4 seconds. So for 4 seconds, this one might see what I've written to Cassandra here, but does not see the Elasticsearch index, which is a complete inconsistency because it completes completely different results as it would do in a 10 seconds later. So this is a time window of eventual inconsistency and complete inconsistency that we took into account and accepted and really spent a lot of time to correct it afterwards. So what does it mean? It means if you go distributed and your customer says, well, I have all these locked uniqueness constraints and everything must be safe, you need to re-evaluate with the customer his requirements. And then there come questions that the customer does not like. For the uniqueness constraint on the relations, the question was, how frequent does this happen? How often will we expect to see double relations in the end? What's the impact on the quality? Is anybody seeing that this relation is double, or is this something very right off the decimal point? Are there other implementations that break because we have double relations? And this would be very bad. Do these violations build up over time? Maybe it's a small number, that is a small error now, but because others are depending on it, in a week it becomes a serious error. And if this is a serious error, should we filter it out at the persistence level, at the API level, or are we allowed to correct it, say, every 2 minutes in a batch job using Spark? These are questions that the business people cannot answer. That's why they're going for ASIC, for transaction security, because they are not trained to think in this objectives. And so it's a difficult thing, it's hard work. But in the end, we decided to go for scalability and reduce the quality as little as possible. So conclusions. So first of all, to answer the first slide, yes, it's not a bad idea to do it. You can transform a transactional application into a big data architecture to achieve scalability. And our practical experience experience is that using a microservice architecture is very helpful here, especially because it allows experimentation, because it's a knowledge game. You really don't know the effects of the architecture on the requirements, so it's cheaper to have something that costs only a sprint to develop, to try out, and say, no, it didn't work out, next one. As to have a huge architecture where you have to redo everything. We do have a serious problem with all these requirements that require locking, require constraints, consistency. So to a certain point, this needs to be taken back. So you cannot get both. You cannot get this huge big data scalability and insist on single points of synchronization. It doesn't work. So the business needs to reevaluate these requirements and accept also the compromises. The alternative is not to get this kind of scalability, not to enter the big data world. So, I'm on time. I do have two further slides of the actual technical compromises we had to go and what we did about it. If I get the time, if I don't.
Just go for it. I don't need 30 minutes. Go for it.
Yes.
Sorry? All right. Good. Yeah. Practical consequences. So what's really happening? One is, I call this phantom reads. This was this picture with the two services running completely in parallel. If one doesn't see what the other is computing because there's this time window of eventual consistency, it creates different results as it would if they were executed in parallel. So in a certain way, the graph becomes locally random. What we did is we kept a journal of all the records imported in their time axis and computed by heuristics time windows where we say in this window we should reanalyze because then this error will be factored out because then Cassandra Elasticsearch are in sync and consistent. What happens with Elasticsearch, this is just a warning for those who want to embark with Elasticsearch, except for lots of other warnings about it, is that sometimes if you do such a stage computing, you cannot read your own write. So this is obvious with eventual consistency. If I have one stage here down in the picture, and the next stage is on a different database node of Cassandra Elasticsearch, I have to wait for the eventual consistency time frame before you can read it. But with Elasticsearch also you have this refreshing interval, which is much longer. And what did we do? One is we get exceptions because we don't find the data we need, and we do exponential back-off retries, which is very expensive. And the other one is, sounds silly, but it works. We put delays between the different computing stages in the chain of, say, 4 seconds. We simply say, this message in the queue is stopped for 4 seconds before the next receiver of this queue would compute it. So the answer time gets bad, but the throughput is very good because we don't have any retries. Then we have the old problem of zombies. Everybody knows about zombie records. If you have parallel updates and deletes, which is very common, imagine a workflow through a BPM system where you have update, 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 job is ready, now this record is moved to the history database and deleted in your active database. And if they overrun each other, it could happen that the update comes after the delete, so it's deleted and then created again, which is a zombie. And our solution was the obvious. We tried to use timestamps to have a monotonic order of the records coming in. This is only possible to a certain extent because the timestamps are not completely accurate, of course, between the systems. But we estimated that if there is no update delete sequence faster than, say, half a second, so we are safe. Uniqueness, what I said is it's very expensive in a distributed system if you have lots of unique things, and we had lots of unique words for our natural language processing. And in the end, we simply said, okay, a language has a limited amount of words. So let's simply take all the documents the customer ever has, create all the words in there as unique records first as a try, and let the system work for half a year and delete those that are not used. So we pre-created unique records as a source. And in the end, the last one is counting in such a system is very expensive. So if you want to count the number of words in your distributed database, and you want to keep that's accurate in all the nodes, computing nodes, you cannot use caching anymore. gives you an unknown error rate. So if you keep the number of words for 10 seconds, and then access and compute a new number of words for 10 seconds, your statistics are wrong. So what we did is we took a probabilistic approach called hyperloglock. This is the software developed by Google, and that creates, using a certain hash algorithm and probabilistic measures, creates a tally of unique things that you put into this hash with a known accuracy. So if you have, say, a 1.8 kilobyte large hash map, you can count up to the 32 number of things in the 2% accuracy. And so we put all the words in there, hashed them, put them in, and had a very precise error rate about the count of words, very, very cheap. So, now I'm really finished.
Okay. Are there any questions? Yes.
So in the beginning you said that this is about moving an existing, let's say, old-fashioned, traditional OLTP type of application to the cloud and getting it cloud ready. In the end you showed a number of steps you had taken, and I kind of lost on the way what that had to do with the cloud. I saw a number of interesting re-architecture decisions and the use of different kinds of technologies, but to play devil's advocate, could I have done that within the J2EE monolith that you showed in the beginning, just by using different techniques and APIs, using JMS messaging, using, I don't know, whatever, you name it, what is there in this package? So can you differentiate the architectural decisions that you made from what is really relevant for the cloud?
Alright, so I said this is not a cloud-native architecture in the way that Solana would see, but it is one of the things what we discovered simply was that the computing platforms, the scalability of the cluster Java enterprise system, irregardless of how expensive the hardware would be, we couldn't deal with. So we said very early on we want to have a microservice architecture to be able to scale out horizontally. And so, yes, we could have used up to a certain level of scalability, not in the petabyte range. We could have used the Java Enterprise Server, a very expensive one, big iron from IBM, and very expensive licenses about WebSphere. But the persistence layer had to be replaced anyway, because we are certain that we couldn't put anything of that in a relational database by this size. So what would be the remaining aspects of the Java Enterprise Server that would help us here? It would be concurrency control, which had a pretty much overhead for our purpose. Most of the Java Enterprise resources we couldn't use, so we've decided to drop this big ballast of a monolithic container architecture to go very lightweight. So this is not really something with the cloud in mind. Simply this was the target, to say we want to be able to put everything in the cloud, in the public, but mostly in the private cloud on the customer side, to be able to run it and scale it. Because we could expect that if you have an automotive company that uses the software, and we have currently big licenses about that, I don't say which customer, and he's happy with that. The next thing that happens is that another company, the daughter company in some European, or in the US or in Brazil, will say, we want this also, we want to be attached to this data source, and here is our 500 terabytes of data, go. And so scalability on a long-term axis was very important. And so that we say, drop all the ballast of the old technology and go as little architecture as possible. This was, to us, spring on microservices. Does it answer the question? If not,
maybe we should take it offline.
Further questions?
When you decomposed the entire application into microservices, what decision process did you go through to know the right size of microservice?
That's a really excellent question. The answer is it depends. No, honestly. The really key decision was to lock data ownership into one of these services. So a specific data should be owned by one service at all, and so that we don't have side access to the same data pool. So it is not that one service accesses a part of the graph and the other accesses the same part of the graph. So it's contained. This was one of the decisions for splitting up services. And the other decision was that we don't want to have too many communication over, say, entities, over sidewise communication channels, so that we don't communicate us to death. So we looked into the software and decided that there are natural components that we can split up. So it's the client API, the import API, the agent API, security, periodic cleanup jobs. And then we came to the import thing, which is really a huge thing. And then we decided that we need to break this up according to these criteria. And this was an experiment. So we started with a big service and decided, no, we need 2 or 3 services. And finally we said, okay, this is going to be a plugin architecture. So that we can say one step here, one step here, one step here, and then chain it. It's difficult, there's no good rule. You have to see that you don't have too many interfaces to other services and don't share data, of course.
Okay, thank you very much for your talk. Let's go to the next one, which is a cross-cloud multi-tenant deployment and runtime engine. It will be given by Andreas